Welcome back to Mechanics and Control of Robotic Manipulator. Last short session, what we have given as introduction to a robot motion control. So this particular lecture, we would see little more. So what that means, we will see like what is kinematic control, how we can actually like do that with a manipulator, and then what is dynamic control. And later on, I will give an idea what is trajectory and how to actually like obtain the trajectory with the help of small, you can say polynomial. So these are the things which we are actually like scheduled for this particular what you call presentation. So we can actually like see this is the thing which I was mentioning. So the intention is actually like here we are trying to focus kinematic control. So in fact, in the live session, we have given a very detail. However, I will actually like try to attempt that here. Then we will talk about dynamic control and then finally we end up with the trajectory generation. So let us actually like move to the lecture as such. So so what are the things would be given in joint space? So the joint space, if I talk about something like position control, so obviously the desired position would be given. But here I said it's supposed to be a trajectory. So then what else would be there in kinematics? So the probably the desired velocity would be there. So in that sense, what one can actually see as a given or the desired. So what are the things would be there? So that would be what you call the desired joint position, because we are talking about everything in joint space. So the desired joint position would be given, which is q desired. Then the desired joint velocity would be there as long the trajectory is actually like just a set point, in the sense you have given a point to point. So this is p1 and this is p2, then it is actually like point to point control, right? So in that sense, the q dot desired would be 0, so that you can actually like take it further. And based on the sensor availability, or you can say based on the system state, so we assume that since it is a kinematic control, we assume that the q of time, in the sense q of t, is available, in the sense the actual joint positions are available. So then further what we can actually expect, probably if the desired thing is actually like given in the task space, so then we can actually like convert with the help of what you call inverse kinematics. And similarly, the velocity also given in the you call operational space, then you can actually like convert into a joint velocity with the help of Jacobian matrix. So in the sense, what I assume that the forward inverse both you call kinematic model and differential kinematic model is available. Further, for our own understanding, I assume that the Jacobian matrices are available, in the sense Jacobian and Jacobian inverse are available to us. So then what else you need to see? So since it's a kinematic control, we are thinking about what would be the, you can say, the joint velocity given to particular joints, so that I can follow the given what you call q desired and q desired dot. So in that sense, what we are trying to find out, the control input here is velocities. So this is joint space velocity. We are seeing actual joint space velocity. This is nothing but q dot. This we are trying to find out. And what would be the easiest way? So you can actually like bring the stability where t tends to infinity. You can actually like say that the q desired minus q tends to 0. Okay. In the sense, what you can say, q tends to q desired when t tends to infinity. If this is the case, what one of the easiest way, I can assume that it is asymptotically stable, where q tilde is actually like, this is I call q tilde. The q tilde is actually like assumed as a exponentially stable condition. So in the sense, what I'm trying to see, the objective as asymptotically stable, where t tends to infinity, the q tends to q desired. In other way, the t tends to infinity, q tilde tends to 0. Where here the q tilde I am defining as desired minus actual. So mostly what we usually does, so q minus q desired, but here we are actually like taking the other way around. Okay, that is the only change. So then what you can see, if the q tilde in this form of exponential, where minus lambda t exponential power, the lambda is as long positive constant, you can actually like assure this, right? So that is what we are actually like looking at. So in that sense, what we are seeing is the first order error dynamics supposed to be stable. So in the sense, this is the first order error dynamics, right? So q tilde dot plus I'm putting as a matrix. So in the sense, lambda q tilde equal to 0. So now you can actually like rewrite that what you call q tilde and q tilde dot. So what that would be? So that would be q desired minus q as q tilde. Okay. Then q tilde dot would be q desired dot minus q dot, right? So I'm trying to use, further I'm assuming that this is a matrix. So for our own understanding, we are assuming that it's a diagonal matrix. Positive constants only would be there in diagonal values. So now we will rewrite that. And this is I don't want, but this I'm rewriting. Why? Because I know that the Q dot is what my control input. So now I can rewrite that Q dot way. So Q dot is Q decide dot plus gamma Q tilde, right? So now we have achieved already what's supposed to be the control activity, right? So here this is actually like proportional control, and this is what you call the desired velocity. So this is we are actually like feed forwarding, and this is actually like feedback. So this is feedback and this is feed forward. Okay. So now you got it like the kinematic control. Now imagine this is all in joint space. Now I'm giving in a what you call the task space. So here there is a typo. Okay, mu dot is j of q into q dot. So now if this is given, what I can do, I can actually like take this mu tilde dot plus I'm putting another variable which is another gain matrix what called gamma. So gamma into mu tilde equal to 0. So what I'm trying to do, so I'm assuming that the gamma as long positive, that to like diagonal values, then this would be definitely error dynamics tends to 0 when t tends to, you can say, infinity. So then I'm rewriting it. So this is what I know already, right? So this equation I'm actually like substituting here. So then what I will get? So I will actually like get, so this expanded. So from there I can actually like find q dot as, so j of q inverse into, so mu dot desired minus gamma mu tilde, right? So this is what we obtained as what you call in the task space, or sometimes we call operational space. So now you see kinematic control is very easy, right? And this kinematic control is very popular in certain cases. What are the certain cases? So if the system is actually like what you call a system is gravity balance, or the system is actually like very, you can say, stable in some of the plane, horizontal plane. Further, what we assume that the inertia forces are actually very much negligible, then we can apply. Either it is actually like in the task space, or you can write it in a joint space, you can do it, right? So now this is done. But now imagine the inertia forces are not negligible amount and the gravity is not balanced. What's supposed to be done? So then we will actually like bring what you call dynamic control. So there actually like we bring the robot dynamic control in joint space. So we are actually like seeing that now the desired is actually like move further, where you can see the desired joint position, velocity, and as well as acceleration would be given. So in that sense, what one can actually like see that these are three given. And as long if it is a set point control, you can assume that these two are actually like zero. So now it is not set point. So then what would be supposed to be available to us? It is second order system. So where you can see that where the you can say actual joint position and actual joint velocity would be available. Okay. So these are easily available. Further, I assume that the Jacobian matrix is available, Jacobian matrix and inverse. And I'm trying to make second order error dynamics is actually like going to be zero in that sense, stable nature. So for that, I am assuming that the inertia matrix and other effect n of q comma q dot also available. So now what I can do, I can do the same thing, but here what would be the input, the tau, what we are trying to find out. So here what would be, sometime even we can write in a task-based form, but what would be the objective? Again, it is the exponential or asymptotically stable nature. But only thing here, not only position error, the velocity error also supposed to be zero. So in that sense, we are defining what is position error and what is velocity error. So now we will come back what would be done in what you call in the you can say kinematic level, that would be gone further. You can see this is similar to what you have done in the first order. Now it is second order. Now if lambda 1 and lambda 2 are positive, as per the second order system differential equation, you know, as long all the coefficients are actually like available, non-zero, and all are in same sign, so then what you can see, the system is stable, right? So in the sense, as long lambda 1 and lambda 2 are positive, and that too like diagonal value, it is definitely a positive, you can say, outcome, in the sense it is stable. So then what you can actually like write, I can rewrite this in the form. So I'll keep it this as it is. This is actually like a derivative term and this is a proportional term. Now I'm actually like seeing that here where the control input comes. So I'm rewriting that here in this form. So now I know this. So can I actually like rewrite this q double dot in the form of tau minus n of q comma q dot whole multiply with the m inverse of q? Yes. So now if I actually like substitute that into this particular equation, so what I will get this. So now I can actually like find this tau, right? So this is what I actually like obtained. So now what this look like? So you can see there is a feed forward term and there are two feedback term, and you can see that the nonlinear cancellation is there, in the sense nonlinear term. So this is what we call computing. So earlier what we call that is a computed velocity control. Now this is actually like computing torque, because most of the conventional manipulator would be rotary joints. So it is computing the torque. So it is actually like what we call computing torque control. So now you can see that this is actually like doing something like weighted, you can say matrix, because that is actually like make sure that your error dynamics is actually like q tilde double dot plus some lambda 1 q tilde plus lambda 2 q tilde equal to 0. So in that sense, what you can see, the system is actually like giving very stable behavior. So this is what we call actually like computed torque control. So wherever you take a control, whether it is actually like computer torque or simple PD with gravity compensation, or you take a simple kinematic control, if you are actually like a trajectory, in the sense the path is with, you can say it is actually like dependent on time, what you call it is trajectory. So now if the trajectory is given, so then you have to use the tracking control. Now we will see how the trajectory can be generated. So for that, I'm actually like taking one simple, you can say case, where the T naught is actually like my, you can say system state would be X naught, and where I'm taking T final, which is I shortly written as TF. So my output supposed to be XF. So now you see this is what the goal, this is the start point and this is the goal point. So how many ways you can do it? As long this TF is given, T minus TF is actually like I call delta T, which is what you call the time taken to reach X naught to XF. There are several ways, right? I can just make it straight line. I can draw like this. I can draw like this. And I can actually like draw like this. There are several ways as long I fulfill the time span, right? But what one can see, the easiest way is actually like you can make a linear, right? But the linear means what would be the, you can say x of t. So I'm writing x of t in this form. So that would be initial plus the slope multiply with the time span, right? So now that would be done. But indirectly what it is giving, so if you are actually like draw the x dot, so x dot you draw, that would be constant, right? So the constant is not achievable directly with the actuator, right? If you connect the actuator immediately, it won't give. So it takes some time to reach, right? So in the sense what one can see, so this is not going to help. So then people thinking about the quadratic, but quadratic is not preferable. Why I will explain. So then what would be the easiest option? I can write in a polynomial way. The polynomial, I start with the third order polynomial. Why it is so? So I can actually like see that the third order polynomial will be having, you can say four coefficients, in the sense four unknowns. So I can take, you can say both initial position and final position. Similarly, initial velocity and final velocity, then it would give four equation and four unknowns. I can actually like solve it. So now if you take fourth order or second order, so the initial condition and the number of equations are actually like not properly matching, right? The number of coefficients in second order system would be three, but I cannot actually like make it that way. So that's why we prefer actually like third order polynomial, fifth order polynomial, seventh order and all. So now you can see that this is the case. So now for a given, you can say initial point and final point, initial velocity and final velocity, I can definitely, what you can do, I can derive this, you can say third order polynomial. The third order polynomial is look like this, right? So now you can actually like go further. So what you can actually get, there would be four equations. There would be four unknowns where a naught, a1, a2, a3. So now I have four equations where x naught is actually like my initial position, xf is my final position, x dot naught is the initial velocity, and x dot of f is actually like final velocity. Okay. So now what I can rewrite, this can be solved in a number of ways. I am solving in a very simple way where I am writing everything in a matrix and vector form. So where this is actually like unknown and this is the matrix which is I call Ax equal to B form. So whereas this A is actually like determinant is non-zero, in the sense A is non-singular matrix. Okay, then I can actually like solve this X, right? So now I can actually like solve this X by taking inverse and multiply this. And with a simplified situation where my initial and final velocity is zero, for example, it's a kinematic control, then the T naught, I assume that it starts from zero as the time step. So then the simplified equation is giving a naught, a1, a2, a3 in this form. So now the generalized case where t naught only I'm starting from 0, but I'm considering this x naught, x dot, both x dot f and x dot naught is there. So then what you can see, you can actually like see that equation is coming in this form. So now you can actually like recall, for example, even you take a 2-hour serial manipulator, I'm giving this is the point and this is the point as x1 and x2. So this x1, y1 and x2, y2. I can actually like make a straight line and I can do a what you call inverse kinematics and I can find q1 of t and q2 of t, right? But for this making straight line, what I can do, I can actually like make this as a, you can say slope. But what I can do, this is actually like also straight line, but I try to make it as a cubic polynomial with this particular case and I can do it. Okay. So in that sense, in the next live class, we will see how this can be done and how you can incorporate in MATLAB. So these all we will discuss. So now you can actually like see these are actually like kinematic case, right? So now you extend to a dynamic case. Then what you can see, the acceleration in this case, it would come as an infinite at a point, immediately goes and come back. In the sense, it is a constant acceleration you have to maintain. This is actually like very difficult, right? In real actuator. Then we can go fifth order polynomial. So that too, like you can assume that initial velocity and final velocity, initial acceleration and final acceleration all become zero. Then it would come as 3, 4, 5 polynomial. In the sense, the polynomial would have only the coefficient would be having only third order, fifth order, you can say third, fourth, fifth order polynomial coefficients only would be available in addition to the initial position. Okay. So these all you can actually like see. So now what one can actually like understand, we have actually taken the robot motion control and then we have seen that if actually like the robot motion control is actually like given as a tracking, so we can derive the trajectory based on the given point and the time span, and then we can apply either kinematic control or dynamic control based on the, you can say, the situation or based on the system nature. So now imagine even you want to do it the dynamic control also in the what you call task space. So then what you can do, you can actually like see, I can actually like recall that. So what you can see like this, you can rewrite in everything in F, and this would be then M, you can say mu, and this would be actually like mu desired double dot, and this is actually like I put gamma 1, you can say mu tilde dot, then gamma 2 mu tilde, and this would be n mu, right? So then once you calculate, then you can actually like take, you can say J transpose of Q into F, that would be tau, right? That also you can do it. So these all we can do it. So in the sense now you can see like how to do a joint space control for a kinematic level and dynamic level. Even you know now how you can do for task space also, right? Or operational space control. But what we have taken a simple first order aerodynamics, stable first order aerodynamics and stable second order dynamics we have considered and we have tried, right? But now you want to do more advanced topics, then you can actually like change this what you call computer torque control, where you have seen this m and n are supposed to be accurately known. Now you assume that these are actually like not accurately known, which I said m cap n cap are the known value, but that is different from original m and n. So then there would be a parameter uncertainty, and in addition to that, this tau is associated with some disturbance. Then you can actually like use some robust or adaptive control. These are actually like what we call advanced controllers. So where you can apply sliding mode, or you can apply probably some optimal control theory, or you can apply learning based control theory. So many things are there. These all we usually cover in robot control system or advanced control system topic. So with that, what one can see, this particular subject, what we have seen. So what is robot motion control and what is kinematic control and what is dynamic control. In the next lecture, we will see how these can be combined as a cascaded loop. And then if time permits, I will show you few, you can say robust or adaptive control schemes for your benefit. Okay. So with that, we will see you in the live session. Until then, see you. Bye. Take care.